there's something I did not include in the slides, but I was thinking this morning, if you are familiar with, do you know why we see the formation so frequently, the formation of disks in astronomy? Because you can have a disk around a black hole, but you can have a disk around a star, any star, for instance, in compact binary systems. But you can also have a disk around planets. You have, for instance, Saturn with the so-called rings, which are in fact rings. Do you know? Do you know why we? Do you have any grasp and idea?
I think it's because we have lots of plasma in the universe, and it's like the formation of disks are related to the rotational energy, and the objects are rotating.
Not exactly related to plasma, but related to rotation for sure. So let's try to draw it here. Okay, so imagine we have a massive body here. Okay. And let's imagine that this body is in the middle of a cloud. Okay, now we have a lot of gas here. A configuration that we will see today is a configuration of static gas that will simply fall in the black hole. We'll see this later. Okay. However, it's basically impossible to have things without angular momentum in the universe. Okay, so imagine that the bulk motion of this cloud of gas is in this direction here. Okay, it's slowly orbiting the black hole. Okay, it can be just a little bit of angular, just almost insignificant angular momentum. Okay, but if it's orbiting, let's suppose this is the rotation axis of the cloud. A particle of the cloud here, the particle is being pushed in the direction of the black hole or the star, okay, of the central mass. It's being pushed in this direction, and we can decompose this force in the x component and the y component. Okay, in the x component, the particle, supposing that it's not interacting with the nearby particles, it cannot move. It has to conserve angular momentum, so it will simply orbitate like that. However, in the y direction, there's nothing impeding this movement. Okay, so the tendency is that this particle will go down. It's being pushed by gravity. Okay, the y component of the gravity. So these particles here, they will all tend to go down, while this here will always tend to go up, and at the end they will form something here. Okay, this is why disks form everywhere. You see disks everywhere in space. And here, to keep the structure of the disk, we need to find a balance, the hydrostatic equilibrium. So you have gravitational pressure compacting it, but on the other hand, you have the gas pressure, the thermal pressure in the gas. And if the disk is emitting a lot of radiation, you have also radiation pressure. Okay, we will see this in this lesson, or maybe in the next one. Okay, let's start with some misconceptions about black holes. Black holes are often thought as the most dense objects in the universe. You probably heard about that. No, you probably, maybe you have this in mind. But this is not true. Well, it depends on how we define the density. But let's talk about average density. If we speak about average density, it's not true. The answer is already there, but do you know why? Because if you have a a star, and the nucleus of the star was being more and more compact over time. And let's suppose after the stellar evolution, it became a white dwarf. A white dwarf is very, very dense. Well, this we all agree. If you put even more mass, we go to an extreme case, crossing the Chandrasekhar mass. You all heard about the Chandrasekhar mass. This is something I would like to teach a lot because it's very beautiful to arrive to the Chandrasekhar solution. However, it has nothing to do with active galactic nuclei. It's a pity. But anyways, so if we cross the Chandrasekhar mass, the white dwarf can collapse into a neutron star, which is for sure much denser. It's unbelievably dense. The average density of a neutron star is higher than the average density of atomic nuclei. So the density in the nucleus of plutonium, for instance, the average density there is lower than the average density of neutron stars. It's really, really dense. But black holes is not exactly the case. So let's take the average density in mind. Okay, this is the radius of the black hole. Have you seen this somewhere else? The Schwarzschild radius. And this is the solution for the horizon of the black hole for the static case. Static means that the black hole is not rotating. Okay, it has no charge, and it's not. It has no electrical charge, and it's not rotating. So this is the solution. You see that the radius of the black hole grows linearly with the mass. This by itself is it's very particular because imagine a sphere of density, of constant density. If you double the radius, what happens to the volume of this sphere? A generic sphere of iron, let's say, a generic sphere here of iron. It has a radius of 1 meter. It will be very heavy. If I double the radius, what happens to the mass of this sphere? Okay, imagine we have a sphere made out of a generic material, let's say iron. Okay, it has a radius of 1 meter. If I double the radius of this sphere, the same constant density of iron, if I double the radius, what happens to the total mass of the... It will increase 8 times. Okay, so if you double the radius, the mass, if you have constant density, should grow 8 times. However, here, it's 1 for 1. Okay, so if the mass doubles, the radius doubles, which means that the volume enclosed by the event horizon will grow linearly with the mass instead of going with the depending on a cubic relation. Okay, so what happens is that the volume enclosed by the event horizon grows a lot, while the mass doesn't. The mass goes linearly and the volume goes with the cube. Okay, so at the end, the density, the average density inside the horizon drops. The more massive is the black hole, the lower is the average density of it. Okay, and you may say, okay, but it's still a astrophysical extreme object. It will be very, very dense anyways. And that's not the case. If you take the supermassive black hole in the center of Andromeda galaxy here, our neighbor, it will be around 1 gram per cubic centimeter. It's like the water density. Okay, this is something that is not in our minds when we start studying black holes. But did you got it? Okay. Okay. Another misconception is that they are vacuum cleaners. The black holes are sucking everything. Everything will fall in the black hole, and this is not true. This is true if this particle or anything is very, very close to the black hole. We see this when we analyze the effective gravitational potential. But in general, if you are in a reasonable distance from the black hole, like hundreds of Schwarzschild radii away from the black hole, the object will simply orbit the black hole normally, okay? And another misconception is that everything inside the black hole is dark. If you cross the event horizon, poof, everything turns off. Boom. No. If you if you cross the event horizon, all the universe above your head is still visible, with the exception that it becomes beamed. Okay. So, and you see some redshift as well. Okay. Okay, so these are just some general misconceptions that people have about black holes. This is I am not derivate the Schwarzschild or a metric here, but probably you see in the course of general relativity. But have this in mind, okay? The Schwarzschild radius. Okay, one fundamental concept in active galactic nuclei is the innermost stable circular orbit. Do you remember from the first class that I showed you some pictures, no, some drawings of black holes with accretion disks? And I say that the disk is not touching the black hole, it's not touching the event horizon. It stops at the innermost stable circular orbit, okay? And then the particles that fall inside that just fall in the black hole, okay? Let's go slowly to find where the innermost stable circular orbit is found. So in Newtonian mechanics, the effective gravitational potential is written like this. This is the gravitational potential, and this is due to angular momentum, okay? So the gravitational potential is this. It has a form that you all saw it in, it's the same thing for gravitational systems or electrical systems. You have something like this. You are all familiar with this. No, this is the potential, the effective potential, and this is the distance, r. So if you have, let's say this is the Newtonian gravitational potential. If your object is here in the gravitational potential, what can you tell me about the orbit of this object? What's the shape of the orbit? Circular, exactly. If the particle has more energy, the particle will be here. Even more, the particle will be here. So here you see that this is the radius, no? So the radius of minimum approach will be R0, and the radius of apoastron will be here, RF, okay? So it will become, this is an elliptical orbit. When we get here, the only possibility is a single R. Let's call it RC, R circle, okay? So here is the point where we are allowed to have a circular orbit. This is this effective potential graphically represented, okay? In relativity, things get a bit more peculiar. So we have this extra term here that depends on R cubed. Okay, this is a purely relativistic effect. And this will be fundamental for understanding the innermost stable circular orbit radius. Okay, so this is the relativistic effective potential, relativistic term. Let's take the minimum, actually take the derivative and equal to 0 to take the points of maximum and minimum. So These are the radius. You are just taking the derivative of this formula and equal to 0. So this is the solution. We have two radius where the test particle can orbit in a circle. This is already very, very peculiar if you have only comparing only with Newtonian gravity, no? So we have to find, there is another point here where there is another circular orbit. You see that this can become a single circular orbit if the term inside the square root is 0. Okay, and this will be very very important for us. If you actually, this value here, L4, is always larger than this. Okay, so when you decrease the angular momentum to a point that it becomes equal to this quantity here, then we have the innermost stable circular orbit. But this will be more, this will be clearer if I show you a plot. Okay, this is the Newtonian effective potential, and this is the relativistic one. These are the stable, the circular orbit points. Okay, if we decrease the angular momentum, look what happens to the potential. Okay, these two points of a circular orbit, they tend to the same point. Okay, here I'm not going, in the simulation here, I'm not going to the final point, but the final point is here in 3 Schwarzschild radii. Okay. Okay, and this is stable, so when it arrives here, it's what we call the innermost stable circular orbit. Yes? This show. Okay. Let me show again. So we have the Newtonian potential, effective potential, and now we have the relativistic effective potential. These 2 points here are the circular orbits. Okay, if we decrease the angular momentum of this test particle, these 2 points will tend to the same point. Okay, which is equivalent to say that the term inside that square root is going to 0. Yes. So when they merge here, this radius is exactly 3 Schwarzschild radii. Okay, and it's what we call the innermost stable circular orbit. Below that, things cannot orbit the black hole anymore. Okay. Okay, so this is basically what I said before. This is the solution. If we take the product here inside the square root equal to 0, we can factor L4, L squared. Here we assume that 0 is not an option, because angular momentum 0 means that the particle is going straight to the singularity. Okay, and in a real scenario, this is basically impossible. Okay, so we always have angular momentum. We ignore this 0 solution, the trivial solution, and then we solve for L here, and we find that the angular momentum, this is the square of the angular momentum, minimum is this one here. Okay, and as a problem for you to do at home, I will ask you to show that the radius of the innermost stable circular orbit can be written as 3 Schwarzschild radii. There is a passage here, but I will give you in the last slide, okay, how to solve that. Okay, we are going to discuss another thing now, which is the Eddington accretion, Eddington luminosity and Eddington accretion rate, which is fundamental for people working with active galactic nuclei. But before going there, I want to ask you, is everything okay, clear up to now? Do you understand the concept of innermost stable circular orbit? Okay. Okay. So, there are these two fundamental quantities called the Eddington luminosity and Eddington accretion rate. which is the Eddington luminosity. It basically resumes to equilibrium between gravity pushing things inwards in the direction of the black hole or accreting, and radiation pressure due to the accretion pushing things out. If the radiation is too intense, the matter cannot be accreted. Okay, so it's a limit where the radiation is blocking the accretion. Okay, this is the Eddington limit, but we'll see it in details now. So for an isotropic radiating source, the energy flux at a distance r from the source, considering it isotropic emission, the energy flux at a distance r will be simply given by the luminosity of the source. This is in energy per second, divided by the area. This is the energy flux. Okay, but for photons, we know that the momentum of the photons can be written as the energy of the photon over c. If we divide S by c, we will have energy per second that will become momentum per second. Okay, but momentum per second, what it is? Force. Derivative of momentum per second. Okay, so you have force. This will be force over area. Force per area is pressure. So the pressure, radiation pressure, can be written as the S over C, which is this final expression there. Now, we have this pressure which will interact with particles which have a cross-section area. For electrons, the cross-section is the Thomson cross-section. Notice that the cross-section for particles can be written like this. And you see that if I put the mass of a proton here, what happens? The cross-section is much, much smaller. So the interaction of the radiation pressure with the particles falling into the black hole will happen mainly with the electrons. Okay. However, what happens if I push away only the electrons and leave the protons? A Coulombian argument. They will attract, it's the opposite, no? If I push only the electrons, yes, the electrons go, but then there is a Coulomb potential between the electrons and the ions, and then the ions follow. So the force, the radiation, the force induced by the radiation pressure will act on the electrons, but at the end, it will blow away everything, okay? Okay, so this is the force acting on a single particle, on an electron actually. And if we take this radiation force and set it equal to the gravity force, we will find the Eddington limit. So this is the radiation pressure force, and this is the gravitational force in the particle. If we solve for the luminosity, we'll have this result here. This is the Eddington luminosity. This you need to bear in mind. This you hear about this everywhere in AGN astrophysics. Okay, and it's much more a threshold case than something really absolute. Okay, you can find super Eddington AGN. Okay, AGNs emitting over these luminosities. However, this quantity here in the screen is a threshold, is a comparison, is your baseline. Okay, so people typically do calculations and measurements in AGN physics, having the Eddington luminosity as a standard. Okay, so bear this in mind. And for an AGN, this luminosity, well, computing the constants here, it will be proportional to 10 to 38 ergs per second times the mass of the black hole in terms of solar masses. Okay, so for a black hole with 1 billion solar masses, we have 10 to 47 ergs per second, which is a lot. Okay, in the sub-Eddington accretion, gravity wins and material falls in the black hole. In the super Eddington, which means that the luminosity is pushing away the gas more than the gravity is accreting it, the radiation pressure is so intense that it blows away the surrounding gas, preventing further accretion. And in thesis, the Eddington luminosity is the maximum luminosity allowed for objects powered by accretion. Okay, but in practice, as I mentioned before, it's not exactly that. We can see some special cases. Now we also can define the Eddington accretion rate. Actually, this one is better if I write in the other man. Okay, we have the luminosity is better is eta c square m dot. This m dot is mass per second. Okay, so mass mc square, we have the total energy of the rest energy of the particle per second. So we have energy per second is luminosity, okay, or power and luminosity are the same thing, no? This eta is just the efficiency, okay? So the Eddington accretion rate is defined as the Eddington luminosity divided by this efficiency coefficient and the speed of light. Measuring this eta is not a trivial task. Okay, we will see this in the other slides. And a very common way to refer to the Eddington accretion rate, to accretion rates, is to write them like this. The accretion rate of this black hole is some number divided by the Eddington accretion rate. Okay. When the accretion rate is in this range, 1% to 30% of the Eddington accretion rate, and we have the Shakura-Sunyaev disk, which is geometrically thin and optically thick. Eta depends entirely on the location of the ISCO, the innermost stable circular orbit. See how important is the ISCO. It will drive observationally. It will tell us where is the continuum of the spectrum. Okay, when you observe the spectrum of an active galaxy, the continuum is coming from the disk. But the radiation from the continuum depends on the temperature of the disk, and the temperature depends on the position of the ISCO, okay, and on the spin, but okay. So for static black holes, the accretion is typically 6%. For intermediately rotating black holes, the accretion is around 10%, and in the extreme cases, the accretion is 32%. This 40% accretion, which would be the maximum allowed rotation of a black hole, such that the singularity does not cross the event horizon and is not a naked singularity, this will never happen. There is this third limit, which is caused by photons in the disk being absorbed by the black hole and breaking its rotation. Okay, it's a very complicated thing to understand. But in any way, this efficiency here of 40% is basically impossible. Okay, we are actually around 10% for an average and you see in a few slides why and how hard it is. So for RIAFs, which are radiatively inefficient accretion flows, the accretion rates are lower than 1% of the Eddington accretion rate. And the thin disk vanish. This is other thing that I can draw, because it will be better to follow. I told you that the disks form like this, no? However, what happens if here we are dealing only with gas pressure. What happens if I have radiation pressure here? And notice that closer to the black hole, we have more radiation pressure. So if we have a lot of radiation pressure here, that the gravity cannot compensate for that, the disk will blow up. Okay, so it will become large, geometrically thick, and you become optically thin. Okay, so this can happen if we have a very low accretion rates, but can also happen on the other extreme. If we have so much gas being accreted to the black hole, it will become what we call the slim disk. But it's another thing that I'm not going to enter in details here. Okay, so the efficiency for RIF is around 10%, depending on the accretion rate. Okay, 10% or less in this case. Okay, how to estimate this eta? I'm showing you so you know that something exists. This exists. Someone tried to do that before, but you don't need to really try to go very deep on this. There is this, I don't know how to pronounce the name of this guy, Sultan argument. It entirely avoids measuring the accretion rate for individual objects. Instead, it's very easy. You don't need to you just have to integrate the total luminosity of all quasars over the cosmic time. Okay, it's so integrate the local supermassive black hole mass function. Obtaining the mass function is already very complicated, and then we have the total mass density of supermassive black holes today. And we assume that the accreted mass density is whole accretion is equal to the density of black holes today minus the density of the black hole seeds. However, we assume that the seeds are were very small masses. Okay, so we basically cut here. By energy conservation, we find this formula for the radiation and energy density, and you can finally isolate eta in terms of these quantities here. The important thing here is just to understand that we can measure this and this, okay, Ho and Urad, okay, although it's not easy, okay, and okay, this is how it's done for. I'm not even accounting for the Ho here. Just showing you how the radiation density is evaluated. So we have this integral here where we have to include the AGN luminosity function, which is already something very, very complicated. Here we have this cosmological term. So this measurement depends on how well we understand the universe. So what's the matter omega and the cosmological constant omega. So it's very complicated, but you can estimate. And when we do so, eta is around 10%. Okay, when you integrate over cosmic time, over the luminosity of all quasars and everything. Okay, it's around 10%. So it says that on average, black holes have average rotations, like 50% of the limit. Okay. Okay. There is this alternative form, which is doing a fit, and this will search for a single AGN. Okay. However, this is not easy as well, because here we are not using Shakura-Sunyaev, the disk model, we are using this Novikov-Thorne model, which is much more complicated because it's a general relativistic solution, while the Shakura-Sunyaev is not. So the black hole mass is measured independently via reverberation mapping. Do you remember what is reverberation mapping? From the first class. This is what Emily, my student of Initiation Scientifica, is doing now. It's measuring the mass of black holes using a sort of reverberation mapping. You remember that we have some burst in luminosity, and then it will reach the broadline region, and then this time delay, we see this time delay in the observations. This is the reverberation mapping. So you can measure the mass of the black hole, for instance, with this method. You can constrain the inclination of the black hole. It can be, well, you can do that in several ways. For instance, observing the oxygen tree line, the intensity of the oxygen tree line, yes, several things. And then you can apply this fit, and the fit will give you the spin and the accretion rate. Okay, so you can recover the spin. But it's not from the fit you can recover the efficiency. Okay, but it's not trivial. It's not. It's really a hard task. Okay, now we will talk about another thing that is fundamental for AGN astrophysics, which is the spherical accretion. Is there is no kind of accretion that is simpler than that. Okay, so imagine you have the black hole inside an infinite cloud of gas, constant density. Okay, time zero, everything is homogeneous, and then they start following the black hole. Okay, this will define the Bondi accretion and Bondi radius, you see. So for a gas particle of mass m at a distance r from the black hole, we have the potential gravitational energy is given by this, and the thermal energy of this particle in the gas will be given by this, where v square is the sound speed, okay, of the gas. Here we just have to, we are just equating these two terms. So if the escape velocity is smaller than the speed of sound, which is the typical speed of the particles in the gas, then the random motion of the particles is not sufficient to avoid the accretion. Okay, so we define this as an order of magnitude definition as the Bondi radius. Do you know this form, this shape? Do you know, does it remind you anything else? Schwarzschild radius, yes. Schwarzschild, there is a factor of 2 here, which is this one here, but we are doing order of magnitude. So it's the same shape as the Schwarzschild radius, but we are using the speed of sound. Okay, so if the particles are not fast enough, they will find the black hole. Otherwise, the temperature of the gas will prevent the accretion. Okay. So the spherical accretion rate is the flux of gas crossing a sphere with the Bondi radius. So we have, if you have density times velocity, just taking the dimensional analysis, what do we have? Density times velocity. We have mass over volume times length over second. Okay, so you have mass cut per area per second flux. Okay, so Rho c is the flux of matter, and this flux to give the total absorbed mass per second we just have to multiply by the area of this sphere. And this sphere is defined by the Bondi radius that we just saw, okay? Okay, so we can substitute the Bondi radius here. That's the Bondi accretion rate. So why is this useful for us? Imagine a black hole that is not an active galaxy in the nucleus of inactive galaxies, like the black hole in the Milky Way. There is gas in the Milky Way. So this black hole eventually accretes some particles. This accretion in a black hole as Sagittarius A star in the center of our galaxy, which is not an active galaxy, is still accreting. This black hole is still accreting because it's immersed in gas. There is gas in the galaxy. So let me put this with a grain of salt. The accretion of any black hole will be at least this here, given by this. Here I put a lambda. This lambda is a correction factor that depends on the adiabatic index of the gas. But even black holes that are not considered active, they are accreting. And the accretion rate is given by that. Okay. And here there are some things which are very interesting. Notice that the accretion grows with the square of the mass of the black hole. Why? You know, it's easy to remember from the first slides. The Schwarzschild radius is linear in the mass, and then the volume increases with the radius. If the radius, if the radius is the surface area increases with radius is square, and then if radius is proportional to mass, it needs to be mass square. So we see also that if the black hole is in a denser environment, the accretion will be higher. Makes sense, no? And if the gas is hotter, which means that the speed, the average speed of the particles is much faster, it will be much harder for the black hole to accrete. Okay, so for a hotter gas, the accretion will drop. Okay, this is the Bondi accretion rate. Bear this in mind. This one is very useful. In practice, it's not very precise. Let me see if I have a slide. Yes, I have a slide about this. In practice, it's not very precise because as the fundament of our assumption that this black hole is immersed in a static cloud of gas. And in practice, it's not going to happen. So if we include angular momentum to this relation, we find that the actual accretion rate of black holes, like Sagittarius A star, is much smaller than the Bondi accretion radius. Okay, but it serves as a standard, as a comparison. Okay, and it also doesn't take into account the black hole winds. We can have winds launched especially by Ryaf systems where the accretion is low. We can have these winds, but this is another story. So the Bondi accretion rate serves as an upper limit on how much mass black holes could accrete under the optimal conditions. Okay, everything clear? One of the major, okay, first let me tell you what they are, then how they are formed. It's just it's similar to solar wind, okay, where you have a lot of mass being blown away from the black hole. Okay, it's thousands of kilometers per second. Okay, and this can happen. This wind can be accelerated by radiation in some cases, or just by accretion, because imagine an accretion disk. There are several rings in an accretion disk. Okay, you can separate it in rings. The internal ring, take a generic one. An internal ring is doing friction in both sides. Okay, and then it loses angular momentum and can drop a little bit in orbit. But on the other side, someone has to conserve this momentum. Okay, so there is someone increasing, some particle, something increasing in angular momentum. So at the same time that matter accretes in a disk, a lot of matter gains angular momentum and is launched from the black hole. Okay. So, but yes. Actually, we see, you can see winds directly in AGN spectrum. When you see, for instance, the carbon-4 line in blazars, in flat spectrum radio quasars or blazars, typically you observe them blue shifted with respect to the red shift of the galaxy. So the galaxy is moving very fast from us due to the expansion of the universe. So we have the systematic redshift of this galaxy. But in comparison to the systematic redshift of this galaxy, you can see some lines with a very small blue shift. Okay, these blue shifts are caused by this by material that is being blown, let's suppose in all directions, but we are observing those that are launched in our direction. No? So you can see a little bit of blue shift in this material. Okay. Clear. Okay. This will become interesting. Let me see. Okay, we have time. The temperature profile of a geometrically thin accretion disk. Where is the disk hotter? At which point it's hotter? Is it close to the black hole? Far away from the black hole? Closer to the black hole? Bye, Pauline. Closer to the black hole. This is also my intuition, actually. But we see that it's almost right. It's right, but Mahomen. Let's see. Okay, so we have the Shakura-Sunyaev disk, and these are the properties. So it's a geometrically thin optically disk. The gas spirals inward, losing angular momentum via viscosity. Some of this gas gains angular momentum and is blown away. Okay, and viscous energy is radiated locally as a black body. So this means that, in other words, we will take any ring, all the rings of the disk, and model it as a black body. Okay. So the disk cannot be modeled as a black body because the temperature is not constant. So, but for each ring, we consider a constant temperature. Okay. And this is an assumption we have here, but it can be proved actually. I'm not going to prove, but it can be proved that half of the work done by the torque is irradiated, while the other half goes into kinetic energy. Okay. Okay, so let's do it. For a Keplerian orbit, the angular velocity is given by this. Let's take the derivative of this angular velocity with respect to r, because this will be useful later, you see. And this is something I'm not proving here, but we can prove with pure hydrodynamics that the viscous shear between rings is given by this formula. Here you see the omega dr, this one here, we use it later. And the viscous torque in an annulus of the disk is given by the stress area, this is force, the stress and force per area, force times the lever, okay? So this is the torque. And the power dissipated by this torque is given by the torque times the speed, okay? The angular speed. So this is the formula, but we have already the G here. This is the total power dissipated. So substituting G, we find this. Now we can substitute this derivative here, and you find this result. Here we have the problem of Ni sigma. Ni is the viscosity of the disk, and sigma is the surface density. It can be shown, there is an asterisk here, it can be shown that Ni sigma is written like this. I'm putting this in the problem list, but you don't get scared about it. This one is a bit complicated. I'm putting it there, but you don't need to do it in this case. The others you need to do. This one, no. If you do, you get 2 extra points in the first oral exam, okay? But just if you want to do that. But in any case, you can prove that the viscous coefficient times the surface density can be written like this, okay? And if you substitute this here, you find that the total, this is the power per area emitted, okay? So this is the amount of energy that will be radiated. However, we are assuming that each ring is emits like a black body. Actually, I'm doing this. When I divide by the area here, I'm dividing by the area of a ring, no? But which is 2p r dr. However, the disk has 2 faces, okay, bare decimile. So the total emission per unit area will be 2 times this, okay? But this is the same for the black body emission for each ring. So the factor of 2 will be cancelled. This is the formula we just derived. And for the local black body condition, 2 times this formula will be 2 times the black body emission. So twice the black body emission is equal to this formula here. When we combine, we find a formula for the temperature. Okay. From here, we already have something. We can already explore a limit. No, if you are in a position of the disk which is very far from the black hole, what happens here? This is the temperature as a function of the distance. No, the distance r. R in is the ISCO. Okay, the innermost stable circular orbit. So what happens if we go to a region very far from the black hole? It's still in the disk. What happens with the temperature? Yeah, it will go down, but if R is too big, this term here will vanish. Okay, these brackets here will become 1, and then the temperature will be a power law. No? It will fall with R to minus 3/4. Okay. Okay, but let's plot the precise formula. Okay, let's imagine the black hole in the origin, and this is the accretion disk. This is the temperature profile. Okay, and see that the maximum temperature, well, it's not exactly in the inner border of the disk. So there's no accretion. There is no friction there. No, it's not being heated at that extreme. Okay, so what we find is that the maximum temperature of the disk is a little bit inside the disk. Okay, and here in this region, the temperature simply falls with R to minus 3/4. Okay, because we are far from the black hole. To find this maximum here, we just need to take the derivative of the temperature function in terms of R and make it equal to 0. Okay, and the result is 49/12 Schwarzschild radii. Okay. Okay, this will be interesting in the next slides. Here are the parameters I'm using. So 100 million solar masses for this black hole, and an accretion rate of 0.1 of Eddington, and an efficiency of 0.1. By the way, this shape, you see that the shape of the accretion disk here, it grows in this direction, right? This is somewhat precise, not very precise, but it's somewhat precise, okay? Although we have a thin accretion disk, it will grow in size further away from the black hole. You see why, okay? Can you already see why? Oh no. Okay, it's fine. Okay, so the R2 minus 3-4 profile, which means far from the black hole. This is what I already told you. So this goes to 0, the brackets go to 1, and then we have this this formula here. But okay, this is just what I mentioned before. Now let's focus in other thing. Let's try to compute the maximum temperature of the disk. So we found that the peak is in this position, 49/36 are in. At the peak, this bracket here will become 1/7. If you substitute, you find this formula for T. You can substitute R peak in terms of the Schwarzschild radii. And if you do that, you have this, then you can cancel here GM with one of the GM here. And finally, yes, taking the values of the constant, we will have this, this value for the maximum temperature. And there is something that I think is very, very special about black hole disks, which is what happens, now I ask you, this is the temperature for these conditions here, 100,000 Kelvin, more or less. What happens if I increase the accretion rate? With the, what happens to the temperature? If I increase the accretion rate, what happens to the maximum temperature of the disk? It's straightforward, no? It increases. So if the accretion increases, the temperature of the disk increases. Okay, but what happens when we increase the mass of the black hole? What happens with the maximum temperature? It decreases. So larger black holes have colder accretion disks. If you take the accretion disk around a stellar mass black hole, the thermal emission of this disk will be in X-rays, the peak, I mean the peak of the emission in the X-rays. If you take an active galactic nuclei, for which the black holes have millions of solar masses, this peak, the peak of the thermal emission will be in the ultraviolet. Do you remember the first class? We're talking about the big blue bump, which is in the blue ultraviolet part of the spectrum. That's why, okay, because we have a very large black hole, then the temperature of the disk drops with respect to smaller black holes, okay? Divida aí, os cabos aí do lado de fora. Eles estão gostando da aula também. Okay, so let's explore a little bit the disk geometry. So the vertical downwards gravitation force on a mass element is given by this. This is the gravity pull in the z direction, okay? This is the density. So we have, yes, we have mass times gravity. So we have the force divided by the volume, okay? Because this is density. But we are multiplying by the volume element here, which is the area in the disk times the zeta component, okay? The z component. So the gravitational force in the z component is given by actually gravitational okay, I forgot the names. Gravitational field, gravitational anyway, I don't care. So the gravitational component in the disk z axis will be gm over r squared times the sin of theta. Okay, theta, imagine the black hole is here, the disk is in this plane, so theta will be this angle here. Okay. However, theta can be written as cateto opposto sobre ipotenusa. Okay. So the opposite, it will be z over the hypotenuse, which is precisely is not r, because r is in the disk. But since we are considering a region far from the black hole, we are approximating r as the other side of the triangle. Okay, so it will be z over r. We substitute it here, find this expression. But this, the square root of this is the Kepler angular velocity. Okay, so we can write this expression, actually gz, we can write like this. Here, if we pass this dA here, what happens to this? Pressure becomes the differential pressure. If we pass the dz, we have here. So differential pressure dz, the differential pressure in the z axis will be minus rho g, but g is written like this. So the differential pressure in the z axis will be written like this. Okay. The total upwards pressure, that was the pressure pushing down the gas in the disk. Okay. The pressure upwards is given by the gas pressure plus the radiation pressure. Okay. Here we will do an approximation where the radiation pressure is not relevant, which is a bit strong, but we will do it anyway. But most importantly, we will assume that the temperature is constant in Z. Okay, so for a given ring of the disk, we assume that the temperature is constant independently of the height of this ring. So when you take the derivative of this with respect to the z-axis, this is constant, goes off. Temperature will be a constant by assumption. These are constants, and then there is just the density which is left. So we have this. When we take the derivative of this, we get 0. A is a constant, is the radiation constant. T is assumed to be, the temperature is assumed to be constant, then the differential will be 0. Okay, so the pressure gradient in the z-axis will be given by this. But this we found in the previous slide, no? So this can be written like this. Now we take this and equate to this. Okay, so if you pass everything there and solve for ρ, you have an exponential solution. Okay, actually you pass z here, but you pass ρ here. We integrate, have the ln, the natural logarithm of ρ, and then you can take the exponential. Okay, so we have the density of the gas decreases exponentially with the height from the disk. Okay, where ρ0 is the density at the disk plane. And it's common to define this quantity here as the scale height. So this exponential that we found in the previous slide will become this, okay? Just substituting that. So this is the scale height of the disk, which means that after that, the density of gas already dropped by a factor of 1/e, okay? For the typical values for the ratio HR, H is the scale height, and R is the distance from the black hole, okay? So in AGNs, the typical scale height, the typical values for these ratios, H over R, are between 10 to minus 3 to 0.1, okay? If they reach something at the order of 1, it's not a Shakura-Sunyaev disk anymore, okay? We have to consider other things. like a slim disk or a RIAF, it depends on the case. And of course, this result is valid only for the gas-dominated region of the disk, which is very far from the black hole. We are assuming that the radiation pressure here is negligible. So close to the black hole, this solution simply doesn't work. Notice that the scale height depends on the temperature, no? And we have a formula for the temperature. So we can take the shape of the disk. Remember that the solution is not valid close to the black hole, so it's valid only at very large radii. So this brackets here goes to 1, okay? And then we have this formula for the scale height. This basically delineates the shape of the disk far from the black hole. So you see that the height of the disk increases with R to 9/8. Okay, so it will not be like in the animation slide that it was a straight line, but it will do something like this. This is the black hole. There is the disk here that we don't know from what we did how it behaves, but we know it's very thin. And far from the black hole, it will do like something like this. Okay. Okay. Now imagine that very far from the black hole, the radiation pressure is negligible, and if you keep accumulating mass, so if the disk becomes larger and larger towards high radii, and there's no radiation pressure to support the collapse, what we see is that there is a point where the disk can start collapsing under its own gravity. It's called this point is defined by this Thomry parameter. I'm not going into details here, but this you can use this to arrive at the radius of self-gravity. Okay, the radius where the disk starts collapsing and forming objects. Like it can start forming stars, for instance. So and we observe, for instance, population of very young stars close to supermassive black holes in the center of galaxies. That it's not a proof of this, but it's an indirect evidence that this phenomenon happens. Okay. So yes, and this also defines the end of the disk. After that, the gas collapses, and it ends up in stars or planets or anything. Okay. And that's it. For today, that's it. We have some problems here for you to do at home. So I want you to show that the radius of the innermost stable circular orbit is 3 Schwarzschild radii. However, you need to use this formula here for the momentum, okay? You can take the viscous dissipation per unit surface area, this one, and show that the maximum temperature is this, which is something that we did in the slide, so you can just follow. And this is the challenge one. If you do that, you don't need to do that. It's not mandatory. But if you do, you have 2 extra points in the first oral exam, okay? So the challenge is to prove this one. This passage, we use it for the, when looking for the temperature profile of the accretion disk, okay? So I simply assumed this there, but you can derive this. And you have a lot of fun doing that. You have the conservation of mass equation, conservation of momentum in fluid dynamics. If you want to do that, have fun. It will be 2 extra points. Okay? Doubts? Marcela. No. Naomi, tudo ok? Mais ou menos. Tá bom. Isso daí quando você refaz em casa, porque às vezes aqui a gente passa muito rápido, né?
Precisa chegar e abrir as contas.
Tem que fazer as coisas devagar, tem que fazer. Por isso que eu quero escrito, sabe? Porque aí se não for escrito, não passa pela cabeça, né? Não fixa.
Aí depois quando eu pego os slides, eu vou abrir fisicamente.
Sim. Agora, pessoal, da aula de hoje, o mais importante para ter em mente é limite de Eddington. Vocês têm lembram mais ou menos o que é? Limite de Eddington. Vai, Paulinho.
A luminosidade para equilibrar a pressão gravitacional.
Exato. Então, é a luminosidade máxima que ainda permite a acreção. Outra coisa, a acreção de Bondi. Marcos? Lembra o que era a acreção de Bondi? Ele tem um buraco negro imerso em uma nuvem estática de gás. E o gás tem uma certa temperatura. Se a temperatura for baixa, muita matéria vai cair no buraco negro. Se for alta, o movimento aleatório das partículas não vai deixar a massa ser acretada.
É circular, né? Você falou que era circular. Uma nuvem de gás.
Isotrópica, né? Isotrópica, isso. Uma nuvem de gás isotrópica. Então, a acreção de Bondi é a acreção que todo buraco negro está sujeito. Até os inativos. Né? Vamos ver o que mais aqui. Marcela, onde é que tem o pico de temperatura do disco?
Um pouquinho depois.
É uma beirinha assim, né? Um pouquinho para dentro. Uhum. Now, Anna, what's the... ok. O que acontece com a temperatura máxima do disco se eu aumentar a massa do buraco para um buraco negro de massa mais alta? Deixa eu refazer. Yes. The square root.
But if the accretion rate increases,
The temperature increases. Yes. And I think these are the most important. I need something to ask her. What time is it? No.
You should ask her if you enjoyed the lesson.
What? Do you remember more or less the shape of the accretion disk? We solved it for distances far from the black hole, but you remember more or less how it will be? Like, what's the shape of the accretion disk? How it works as a function of the radius? You remember even the power? Okay. Yes, the most recent one. So, yes, everybody. So I think that there was a lot of information today, but all of this information is very useful if you are doing AGNs. Okay.